Hi, this is Aaron Coleman for Santa Monica Group A. Our proposal consists of a two-stage approach to protect the Santa Monica Pier. The first being a breakwater, which is necessary to protect the pier from a tsunami, which is inevitable due to the impact occurring in the Pacific Ocean. The breakwater will be built from reclaimed concrete rubble, which is available locally in abundant stockpiles for low or no cost. It will be constructed in interrupted segments in 2 rows. The first row to break the wave, and the second to deal with any overtopping waves and to smooth out the water further. The breakwater will then be topped by natural stone boulders to keep the look consistent with the vernacular breakwaters and seawalls in the California coastal area. The second phase of our proposal is to enclose the entire pier in a elongated geodesic dome made from stock storefront aluminum in 10-foot lengths, being the longest length, and glazed with polycarbonate glazing. The 10-foot length makes efficient use of the 20-foot stock lengths of storefront aluminum, as well as the 10-foot by 12-foot stock sheets of polycarbonate glazing. The geodesic dome structure will sit on a foundation consisting of driven steel piers every 20 feet along the perimeter and capped by a steel ring beam, probably from a wide flin beam, possibly from a box section beam. The beam will be welded to the piers, and the dome structure will then be bolted onto that beam.
Hi, this is Elizabeth Stone, and I will be adding on to what Aaron said. With our elongated dome, we need to have this built before disaster strikes, meaning it has to handle drastic temperature changes as well as enormous loads. As he said, the triangles making up the dome structure will have 10-foot spans with aluminum 5052, which is already incredibly strong and resistant to erosion or rust caused by salt water. This means the depth would have to be at least 5 inches for those 10-foot spans, and the steel piers just outside the perimeter of Santa Monica will have 2507 super duplex steel, and for 20-foot spans such as that, it would be 10-inch, if not 12-inch thick steel beams supporting the load. The reason we would be using the super duplex steel is because they use that in the newest oil rigs, which deal with incredibly saltwater environments. And it's way more resistant to rust than normal steel, and it's incredibly strong and will easily support the entire structure, no matter what we throw at it. Everything will be reinforced and anchored into the ground below the pier, just so we don't have the dome fly away. We chose an elongated instead of perfectly spherical dome because Santa Monica Pier is 4 times as long as it is wide, and a regular dome would be a huge waste of materials. Domes are a better shape in general for designing with because they automatically help with reducing snow buildup and are aerodynamic, and our elongated dome would have 2 or more vents near the bottom and a modifiable opening at the top that can get bigger or smaller to allow more or less air. Basically, fresh air would come in through the bottom vents and it would circulate through the base thanks to the shape of the dome, and then once it got warm and stale, it would go up to the top and be vented out the top. In the wintertime, when we wanted to be warmer inside of the dome versus cooler, we could have that opening at the top way smaller, which would get started the greenhouse effect inside of the dome so that it warms up continuously thanks to the sun radiating in through the polycarbonate glazing. And we could put solar cells on top to help with a little bit of shading and also for any electricity needs for Santa Monica Pier, assuming we are talking about a meteor winter, not a nuclear winter, so we still do have sun. And this will help the dome retain heat, electricity. We've got almost everything covered.
This is Madison Beck speaking, and I will be giving a breakdown of how we found our snow load and our wind load. In order to calculate the wind load and the snow load, we had to first find the surface area of our oblong geodesic dome. Our geodesic dome is part sphere and part cylinder, so we used half the surface area of a sphere, formula is 2 pi r squared, and half the surface area of a cylinder, for the formula it was pi times radius times height, We then found our total surface area to be 323,094 feet squared. Next, we used the formula surface area times pressure for wind load, given that the pressure was 50 pounds per square feet. So then we found that our wind load to be 16,154,700 pounds. Then for the snow load, we used the formula thickness of snow, which we said was 1 foot or 12 inches, times the involved surface area times the uniform pressure, which was given that it was 25 pounds per square feet. We then found that the snow load was 6,361,725 pound-feet. This concludes our video. Given that the updated Santa Monica plan now has 2 breakwaters surrounding it, protecting it from tsunamis, and a geodesic dome encapsulating it, protecting it from other elements, we believe that this is enough to save the pier from any end-of-the-world events, as long as they're not pandemic-related. Thank you.